Welcome to the lecture of integer programming problem. The mathematical formulation of integer programming problem will be like this. We will have an objective function. It will be maximize or minimize. Z equal to c1x1 plus c2x2 plus etc. cn xn. It is subject to the constraints a11x1 plus a12x2 plus etc. a1n xn, which may be less than or equal to, greater than or equal to, or equal to b1 a21x1 plus a22x2 plus etc. plus a2nxn less than or equal to, or greater than or equal to, or equal to b2, etc. am1x1 plus am2x2 plus etc. amn it is less than or equal to, or greater than or equal to, or equal to bn. So here this x1, x2, etc. xn will be a positive number. These values are positive. Also x1, x2, etc. xn are integers, some or all. That is, decision variables are integers. There are different types of integer programming problem. First one is pure integer programming problem, that is pure IPP. When xi is an element of zi, zi means it is the integer value for all I. So all values are, all decision variables are integers. That is pure IP. In some cases, some of the decision variables are integers. This type of integer programming problem is known as mixed IPP. Then another type of integer programming problem is 0, 1 IPP. Here, xi will be an element of zi for all I. Also, xi must be an element of 0 or 1. This set must be an element of this set. So these three types of integer problem are there. So first question. A hotel operating 24 hours has the following minimum requirements of waiters. Period 1, 2, 3, 4, 5, 6. Time 7 to 11, 11 to 3, 3 to 7, 7 to 11, 11 to 3, 3 to 7. So minimum number of waiters required during this time is 6, 12, 8, 6, 5 and 3. A waiter reports to the hotel manager at the beginning of the period and continues to work for 8 hours. So formulate the problem as an integer programming problem to minimize the total number of waiters required. So here we can consider this is the decision variable actually. It is minimum number of waiters required. How many waiters are required? We are having 6 time period. So we can choose x1, x2, etc. x6 be the number of waiters required at the ith period. So xi is the waiter required at the ith period. So what will be our objective function? So we need the minimum requirement of waiters. That is, we need the total number of waiters during that time. So our objective function will be x1 plus x2 plus etc. is x6. So what is the next step? Criteria is, so here we are having at the first period, that is the time between 7 and 11, we are having 6. During this time, we have 12 workers. That means during this time we have x1 workers, during this time we have x2 workers. So x1 plus x2 must be greater than or equal to 12. And this is x3 and this one will be x4. This is x5 and this is x6. So during this time we are having x3 plus x2. That is we are having 8 workers here. So our next constraint is x2 plus x3 greater than or equal to 8. Okay. During the next period, we are having this much workers. That is, we need to add x3 and x4. So we can add x3 plus x4 because our constraint is a waiter reports to the hotel manager at the beginning of the period and continues to work for 8 hours. That means the worker before this time period will be present at that time because 3 to 7. Here it is 7 to 11. So x3 plus x4 must be greater than or equal to 6. Next time period is, next constraint is x4 plus x5 greater than or equal to 5. This case, this 5. Okay, next case. Next we need to consider this time period. So x5 plus x6 will be greater than or equal to 3. So finally, between 3 to 7, we need to consider this between 3 to 7 and 7 to 11. So at 7, we are having x1 and x6 workers. So it will be greater than or equal to 6. So since it is an integer programming, all xi will be greater than or equal to 0. And xi will be an element of z for all I. Next question. A company manufactures 3 products P1, P2 and P3 which yields per unit profit of rupees 200, rupees 400 and rupees 300 respectively. Each of these products is processed on 3 different machines. The time required on each machine per unit of the product is given below. So we are having product P1, P2, P3 and we are having 3 machines, machine 1, machine 2 and machine 3. The time required on machine 1 is 30 for product 1, 40 for product 2, 20 for product 3. Here it is 20, 10 and 10. For machine 3 we are having 10, 30 and 20. The time available for machine 1 is 600 and machine 2 is 400 and machine 3 is 800. How many products of each type should be produced to maximize the profit? So fractional units of product P1 and P2 is not allowed. Okay, how will you solve this problem? So it is given that fractional unit of product P1 and P2 are not allowed. Fractional unit of P1 and P2 are not allowed means it is an integer programming problem. So here we are having 3 products P1, P2, P3. So let x1, x2, x3 be the units of products P1, P2, P3 respectively. And it is given that which yields per unit profit. That means this one is the objective function. So for product 1 it is 200, for product 2 it is 400 and for product 3 it is 300. So how will you write the objective function z equal to? It is given that x1 is the unit of product P1. So 200 into x1. Here it is 200. So 200 into x1 plus 400 into x2 plus 300 into x3. So we need to, yield means we need to maximize. So maximize. So this is the objective function. Subjective, we need to write the constraint. 30x1 plus 40x2 plus 20x3. It will be less than or equal to 600. Another constraint is 20x1 plus 10x2 plus 20x3 less than or equal to 400. And another one is 10x1, 30x2, 20x3 less than or equal to 800. So these are our constraints. and it is given that these products cannot be fractional. So it will be integers. So xi will be greater than 0 for all I. X1 and x2 are integers. It is given that fractional units of product P1 and P2 are not allowed. Okay, next question. Four items are considered for loading on an airplane which has a capacity to load up to 25 tons. The weights and values of the items are as follows. Items A, B, C, D, weights 2753, values are given as 10, 36, 25 and 14. Which items and what quantities should be loaded on the plane so to maximize the value of the cargo transported? Formulate the problem as an IPP. So we need to formulate this problem. Okay, how will you write this IPP? So we have three items, not three items, four items. This is X1, X2, X3 and X4. So we have X1, X2, X3, X4 be the number of items A, B, C, D that are loaded on the plane. So it is given that we need to maximize the value of the cargo. So in our objective function we can write maximize. Maximize is equal to, so this is our value 10x1 plus 32x2 plus 25x4 plus 14x4. This is the objective function. Subject to 2x1 plus 7x2 plus 5x3 plus 3x4. It is less than or equal to maximum load is 25. So this one is less than or equal to 25. The item can be 0 or 1. It can be not loaded or loaded. So xi equal to 0 or 1. This one is an example for 0, 1 IPP. The first problem is based on pure IPP and the second problem is based on mixed IPP and the last problem is based on 0, 1 IPP. So methods to solve IPP problems. First one is branch and bound. So here IPP with two decision variable. Next one is fractional cut method or Gomer is constant. Here also we are having two or more decision variables. So these are the two methods to solve the IP. Also we can solve the IPP problems using graphical method. So we can go through one example. A farmer has to plant trees of two kinds A and B in a land 4400 meter square in area. Each A tree requires at least 25 meter square and B tree at least 40 meter square of land. The annual water requirement of A is 30 units and B is 15 units per tree, while at most 3300 units of water is available. The return or tree from A trees is expected to 1.5 times as much as from B trees. What should be the number of trees of each kind so that the expected return is maximum? So here we are having two types of trees. So let x1 be the number of trees of type A and x2 be the number of trees of type B. So two types of trees are there, A and B. So it is an integer programming problem. So x1 and x2 is greater than or equal to 0 and all are integer. Maximize z equal to 3x1 plus 4x2 subject to 2x1 plus 4x2 less than or equal to 13 minus 2x1 plus x2 less than or equal to 2, 2x1 plus 2x2 greater than or equal to 1, 6x1 minus 4x2 less than or equal to 15. x1 and x2 are greater than 0 and x1 and x2 are integers. How to solve this problem. We had already studied about this graphical solution method. So our feasible domain is A, B, C, D, E, F, this magenta polygon. So we need to find the points. So this point is unknown. So C is, that is optimal solution is x1 equal to 7 by 2 and x2 equal to 3 by 2 with z equal to 33 by 2. On rounding off, we will get 7 by 2, 3 by 2 to nearest integers. There are 4 feasible points. On rounding off, we will get 4 feasible points. Here it is 3.5, right? So on rounding, our points are 3.5 and 1.5. Rounding this one, 3.5 means 4 and 1.5 means we will get 2. Also, we can drop this one. So we will get 3. Drop 0.5, we will get 0.1. Also, we can consider this point. So we will get 4. We can drop this one. So we will get 1. Again, drop this one, 3, and round this one, 2. So we got 4 feasible points. That is 3.5 is between 3 and 4 and 1.5 is between 1 and 2. These last 3 points are not feasible. So it is out of feasible region. So the only feasible obtained point is 3, 1, which makes z equal to 13. This is our linear LPP. How will you solve it using integer programming problem, IPP? So here we restrict x1 and x2 be the integers. The set of feasible solution are the points in the polygon A, B, C, D, F whose coordinates are integers. Such points are A. A means 1, 0, 2, 0, 0, 1, 1, 1, 2, 1, 3, 1, 2, 0, 1, 0, 1, 2, 2, 2. Among these points, the objective function z is maximum is at 2, 2 with z equal to 14. Here we got z equal to 13. If we are solving this problem using linear programming, we get z equal to 13. But if we are using z equal to linear programming model, then we will get z equal to 14. Thus, rounding off gave a wrong answer. Here we are using rounding off solution. It gave a wrong answer. Feasible region of integer linear programming is convex or not? No. Convex hull of this non-convex feasible region is shown in green region. What are the conclusions? Actually, the optimal solution of this problem is 2, 2, which is the optimal solution of the given linear programming problem. So, in both cases, we got the optimal solution as 2, 2. Thus, the optimal solution of a integer LP is same as the optimal solution of a linear programming problem whose objective function is the same as that of the linear programming problem, but whose constraints are such that the convex set of the feasible solution turns out to be convex hull of the set of linear solution of the integer programming problem.